All right, real quick, let's do number 25 on page 67, chapter 3. It says, determine how much farther a person can jump on the moon as compared to the Earth if the takeoff speed and angle are the same, but the acceleration due to gravity on the moon is 1/6 of that on the Earth. Okay, notice they hardly give you anything, huh? But they want you to compare two things. I'm going to show you a trick. Here's given. So this is the same picture on the moon or on the Earth. We're going to launch with a certain initial velocity, and we have a certain launch angle. Now, we know that the acceleration on the Earth, I'm going to call that a sub e, and the acceleration on the moon is equal to a sub e divided by 6. And we want to find, how does the maximum displacement from here all the way over, so it's going to go whoop, like this. How does this delta x on the moon compare to delta x on the Earth? So I'm going to express it as a ratio. Let's solve. Okay, well, delta x, whether it's on the moon or the Earth, depends on the initial velocity of the x times time for both of them. Well, let's figure out how much time that takes to go up and down. If you go up and down, well, then your delta y equals 0. So I can say this, delta y equals v naught t plus 1/2 a t squared. But if we go up and down to the same height, delta y equals 0. So I set that equal to 0. Now I'm going to take this and solve it for time. The first thing I'm going to do is divide both sides by time. And zoop, zoop, zoop. And so now we have delta y equals 0, and that's going to be equal to v naught plus 1/2 a times t. So let's solve for t. T equals negative v naught times 2 divided by a. All right? So now I'm going to take this and substitute it in here. And so I'm going to do this. So delta x, am I still on screen? Because that's what I messed up last time. Delta x equals v naught x times t, but t is equal to negative v naught times 2 divided by a. So now I can set up the ratio. So delta x on the moon divided by delta x on the Earth is equal to, well, delta x on the Earth is v naught x, but that doesn't change. We said that the initial velocity was the same, minus 2 v naught over the a, but this is on the moon, divided by delta x on the Earth. Well, that's v naught x times t, but t for on there is negative 2 v naught, but this is the acceleration on the Earth. Now this looks messy, doesn't it? It's the opposite of messy. It's wonderful. Because now I've got a numerator and a denominator, and almost everything is the same. So what happens to it? It cancels out, cancels out, cancels out, cancels out. Oh, wait a minute. We got 1 over the acceleration on the moon over 1 over the acceleration on the Earth. So delta x on the moon over delta x on the Earth is equal to, well, reciprocate and multiply. This is 1 over this times on the Earth over that. Now, but we said this, we know this, that the acceleration on the moon is 1/6 of that on the Earth. So we're going to say this is on the Earth divided by the moon, but that's a over e divided by 6. So this cancels this. I have 1 over 6, so that's 6. So the answer is 6. So the distance I travel on the moon is going to be 6 times the distance I travel on the Earth. Now, wouldn't that be awesome? If you could jump 6 times farther on the moon than you can here. What if we we had a big gymnasium on the moon. We put air in there so you don't die. And you go running and you sprint and you jump, you're going to go 6 times farther than you would on the earth. If you're a volleyball player and you leap up to block a shot, you're going to go 6 times higher. It would be fun. Let's go to the moon.